Hello. My talk is going to be pretty low level, so I hope you will get a lot of fun. My name is Ivan Mamontov. I come from Russia. I'm search engineer at Great Dynamics. For the last few years, I have been working on e-commerce search solutions, platforms. And today I'm going to give you some high-level introduction to Lucene index, what does codec means and how it works internally. Also, I will provide some information about vector and scalar operations and how can we use them in Java and what can happen if you use them in Lucene. As you know, Lucene is document-based information retrieval system. It can search among of millions of documents at a time, and so as a result, it have to store this index on the disk because it doesn't fit into memory. And use this index on demand. In order to reduce disk latency, Lucene uses sophisticated techniques to compress this data. In order to reduce index size and minimize I/O, so it can. As a result, we can effectively use file system, memory, and CPU caches. Why should we worry about caches? Why should we need to compress data? Because for modern computers, the basic mantra is fast memory is expensive. So modern computers have a lot of hierarchies have complex hierarchy of caches, and I mean a register. We have registers, levels of caches within the CPU, like L1, L2, L3 caches. We have data caches, instruction caches. HDD caches, and the operation system has caches too. Caching is one of the main methods to reduce the latency of to reduce the impact of latency. So on this picture, you can see how it costs to read data from each level of cache. So if we is our data fit into L1 cache, we need to about 5 of nanosecond to reach this data. Instead of from disk, we need to spend about millions of nanoseconds. So if we have compact data, then the data we have high probability that this data can fit into the memory, into one of the cache. So as a result, we can reduce the latency of our algorithm and the search, for example. For this purposes, since Lucene 4.0, there is a special layer. It named Codec. It completely separates index and search logic from storage. So if you want to read something from index or search something, you have to call Codec API. Codec determines how and where files are stored, and it will separate the logic from storage. Let Let me introduce you into Codec API. Codec API has 4-dimensional. For example, if we if we try to search a term query for title Fox, first of all, Lucene tries to find a field in field enums. Then it tries to find term in term enums. Actually, it is a kind of hash map lookup. And then, when we find a field title and term Fox, title Fox, we have to read the posting list. As posting list actually encoded in Lucene because we want to fit into cache. So if we have a high frequency term, we have a huge posting list. It takes about hundreds of millions documents. So the most time of in this case we spent a lot of time in reading this posting list and then decoding them. So this is the main part of our algorithm. Let me introduce how posting list is encoded in Lucene 5.0. Lucene 5.0 is default codec for Lucene. Lucene uses encoding with 4 delta algorithm. It uses deltas. It doesn't store original values, it stores only deltas. Lucene split posting delta list into blocks of 188 values. For each block, it applies bitpacking encoding. I will explain how it works later. And if we have a posting list which not is multiply of 188, when the remaining docs are encoded with variable int encoding. Let me explain how it works on a very short example. In this example, we have a block size 4. We have following numbers 1, 3, 4, 6, 8, 20. First of all, we are calculating the deltas between each values. We store first value, and then we calculate deltas. 3 minus 1, 2, 4 minus 3, 1, etc. So after that, we split all these deltas into slices with 4 elements in each. And the last 2 values we store as variable int. If you want to know more about variable int and how encoding works, you can speak it, hear it about tomorrow. Today I am trying to explain how a P4 works, actually P4 works. For example, we need to encode the following 4 numbers, 1, 2, 1, 2. First of all, we need to find the maximum value, calculate how many bits required to encode this value, and then we write every value in this block by using we write at the head of this block number of bits per value and then encode every value with bit size. So for this example, for encoding requires 1 byte instead of 16 bytes. 4 bytes for every integers takes 16 bytes. But now we are using only 1 byte. So for our first example, if we don't encode these posting lists, we will use 40 bytes to store this posting list. I mean 10 numbers, 4 bytes for every number. It takes about 40 bytes. In our case, we spent 1 byte for this block, 3 bytes for this block, and variable bytes. So it takes about 10 bytes for, in this example, more than 4 times. We compress it at 4 times with posting list. So we have quite good compression rate. We can decode our posting list as fast as possible because we don't need to read each byte each other. In our codec, when we decode this block, we just read block's header, multiply this header on amount of elements in the block. So 2 bits we multiply on 4, and we read 1 byte. Then we can decode this block in CPU as fast as it's possible. Also, this codec can be vectorized. We can do all this operation on CPU side without any interaction with memory. We can do it on large registers and speed up this algorithm. Actually, unfortunately, this algorithm has some disadvantages. For example, we cannot random access within the block. We cannot read a value without decoding all the values in the block. Also, compression rate is determined by the largest deltas in the block. So we have very density data, we have low compression rate. Let me step away and describe what vectorization means and why it can improve performance. Consider the following example. In this example, we have 3 massives with 4 elements in each. And we have a simple loop where we just sums these arrays. In case of Java HotSpot, JIT compiler will provide about 30 true machine instructions. This is not a Java fault. Java is safe language, so it produces bounds checks, it checks null pointers, it's doing some unrolling, peeling stuff, so it produces a lot of instructions. In case of C language, GCC will produce 24 instructions in Scalar mode. So when if we provide to GCC compiler some hints, it will produce a Scalar variant of this code, and it will produce 4 machine instructions with using SSE instructions. So in this case, we just load 1 vector, load 2nd vector, something, and store the vector into memory. Here I describe how it works. In case of Java, we load every value of massive of array, summarize it, and store the value. So we should do it step by step, and also it is required to put registers, store register, move register. There are a lot of stuff which we should do in Scalar mode. In vector mode, we just load vector into special CPU register, do our operation, and store this value into register or main memory. Also, we can put this value into other register and calculate it in chain. In this case, we have 75 fewer loads, 75 fewer adds, and 75 fewer stores. So in best cases, in our case, we have 4 times faster algorithm, and it works 4 times faster. But what about Java? Lucene is written on Java, so we have to use Java. There is 2 ways to vectorize any algorithm: implicit and explicit vectorization. So Java supports only implicit vectorization. It means we have to write our code in Scalar way. We don't use any CPU intrinsics. We don't use some public API for vector operations, and we rely on compiler. And compiler at compile time decides what to do, what operation is it a vector operation or not vector operation. So it's a kind of pattern recognition. We cannot, if we swap 2 lines of code, we can break the pattern, and compiler cannot produce vector code. It just interprets. It just produces a scalar code. Now JVM HotSpot team tries to introduce basics of vectorizations, and now vector arithmetic is not supported, only in simple cases. Java mostly uses vector in array initialization and array copy. So it's not. It will speed up code, but not as can. Explicit vectorization does not support it by JVM. It means JVM does not provide any annotations, compiler hints, which can generate vector code. In C++, we can write our code in assembler, or we can use CPU intrinsics, vector libraries, and compiler will provide code for target platform in vector mode, or else it fails and log a warning message about broken vectorization. Also, not all algorithms can be vectorized, because vector arithmetic doesn't support if statements. If we have a few statements if statements in our algorithm cannot be vectorized, because we cannot apply if statement for every element of array. There are some workarounds like bit masking, but they work bad. So if we have if statements, our algorithm, our performance of using vector arithmetic is completely gone. As a workaround, HotSpot team provides the following solution. They recommend to write code or kernel code in C, C++, compile it for target platform, and call via JNI, Java Native Interface. In this case, it works, but if our duration of our method is low, we can measure it in nanoseconds, then the cost of GNI call can be significant, and we lose our boost. What makes GNI call significant? On every GNI call, JVM should wrap every object into a wrapper. It should logs monitor, check exceptions, unwrap objects, and return values, convert values and return. So there are a lot of stuff which JVM have to do when we call GNI method. It's very, it have significant overhead. For internal purposes, JVM team, compiler team, and JVM team uses private interface. It is almost private. We can use it. And it presents in Java 7, Java 9, Java 8, maybe in Java 10 it will be. Java Critical Native. This is a kind of hack. This method doesn't allow to call native routing from the Java code, but it reduces cost of GNI method call. How can we? What was reduced? Critical method static and not synchronized, because we have to move parameters as parameter GNI call object reference. It doesn't throw exceptions. It does not use wrappers, and it works with primitives. Only primitives are allowed, so we cannot manipulate with Java classes. It just provides a reference on the array from the heap into our C routine, so we can work with array from Java heap and do with it anything. JVM does not check what we do with. We can do what we want with array. You can see more details about this feature. Maybe in future it will be public, but now it's in test and uses by JVM to encode and decode some critical, performance critical features. Actually, a critical method, critical native executes only Java, creates native stack, put parameters in abstract application binary interface, and call the native function. All these overheads are completely gone. So its look sounds great. So let's check how it works. How it works. As a reference implementation, I get a native for simple C library from GitHub. Thanks to Daniel Lemieux, Landin, Baltsov. Actually, Daniel writes his simple library. It utilizes simd instructions. It uses C99 syntaxes, so it can be compiled at any compiler. It supports any kind of vectorization. We can provide. We just can provide a target platform, and it will generate optimized code. This code is quite simple. It works. It can utilize about, in best cases, about 10 operations per clock, instructions per clock. So in Scalar mode, we can utilize only 4 integer operations per clock. In this case, we can utilize about 10 instructions per clock, because SIMS registers are very wide. There are a lot of registers. Modern computers have a lot of registers because games, videos, music drive a computer. Modern CPUs and CPUs use a lot of vectors internally to speed up games and films. In my benchmark, I used Java Microbenchmark harness. It's a great tool, thanks to Alexei Shipilov. It helps to avoid common microbenchmark pitfalls like a JVM warm-up. It controls any JVM stuff like a GC, like it can provide any useful information about instructions, which instruction I used, where is bottleneck. It can disassemble benchmark and say what happened. In my benchmark, I used Java variable int implementation. This is classical variable int implementation. I used it as a reference implementation just to show how variable int works. Also, I have Java 4 implementation. This is classical 4 implementation, which written on Java and used by Scalar, Lucene. Sorry. Also, I write GNI wrapper, which calls native form implementation. And there are two modes. Normal GNI, as it calls GNI as usual, and critical GNI, which use critical native feature. My environment is pretty modern. It uses the last CPU family, Haswell, to utilize huge vector instructions. Modern Linux kernel, latest official Java, and modern GCC compiler for native implementation. In this experiment, I decode blocks with fixed size. I use a different size and measure latency of each call. Every block contains random elements with fixed density. It is important to fix density because for algorithm depends on density of data. So if we have if density will different between measurements, we will fit into L1 cache or L2 cache, so our experiment will have a big jitter between results. So when I fix density in this experiment, density is 10. It means every element not bigger than 10. The maximum delta between elements in this experiment is 10. So here results. The most important column result is in block size 138 because Lucene uses this block size. As you can see, the y-axis is decoding latency. High means worse. Low means better. So in case of critical GNI call, we have latency about 70 nanoseconds per call. So we decode 128 elements in 70 nanoseconds. In case of normal GNI call and blue Java 4 call, for block size with 138, we have the same latency. It's about 180. It's 2 times bigger than critical call, and they show the same latency. So in case of Lucene, codec, standard GNI call has significant overhead and doesn't improve performance. In case of critical call, we improve performance of decoding in 2 times. Be careful, scales are logarithmic, and I tried to find where is GNI call be as effective as critical call, and it is effective in very large blocks, and I think it is impossible to decode values in such large blocks. So. So these results are more than expressive. We can improve performance of our decoding of posting list more than 2 times. So we can write our own implementation of Lucene codec, which is based on Lucene 5.0 codecs. In our case, we just we have to change 4 utils, Java 4 utils on our native 4 utils. It's not a big deal. So as a native implementation, I'm still using Daniel Lemier's codec. this codec doesn't support frequencies, positions, offsets, and payloads. It's because I have no time to finish it, but I hope I will. Source for this code also available on GitHub. I think I will create a patch for Scalar, for Lucene, and publish this code as patch. For benchmarking, I use Lucene benchmark. This is well known, I think, framework which benchmarks Lucene internals. This benchmark indexes all of Wikipedia English XML export. It indexes only documents because we don't support term frequencies and positions. It uses one large segment, because if we have a lot of segments, we have we didn't win from this from our encoding, because a little segment mostly encoded in variable in, because blocks we cannot create blocks with 128 elements. So this encoding is effective in case of large segments. This benchmark measures how long it takes to search top 10,000 frequent terms. I have excluded stop words because they are the most frequent terms, but they hit some Lucene internals. In case of stop words in high frequently elements, Lucene didn't encode it as P4. It just marks as all elements are equals and encodes in 1 byte. This is intrinsic of Lucene. So if we have very frequent element, for example, stop word the, it contains any element, so all deltas are equal, and Lucene writes 0 value. It means all elements are equals, and it didn't compress anything. So in order to avoid this intrinsic, I exclude from this experiment these words, and it's quite tricky to find elements which does not fit this intrinsic. But in real case, people doesn't search stop words, and so these top 10,000 elements looks like real cases, search cases. I do this experiment on the same environment. If you want to repeat this experiment, you can check out my code, compile native implementation, and run on task. Also, I have provided algorithm, my own algorithm with my files. Here is the results. In case of Lucene 5.0 codec, which is default, it takes about 60 seconds to search top 10K elements. In case of my codec, it takes about 49 seconds. The total win is about 18%. I think it's a good boost. This result looks good. The most in case of my codec, the most time Lucene calculates, sorts the heap. So the other time of the other 39 seconds, Lucene mostly sorts heaps and put elements in heaps and returns elements from the heap. So the time what codec is spent in encode and decode was significantly reduced. Both codecs produces the same index. Index is compatible, binary compatible between two codecs. We can encode it by Java codec and read by native codec and vice versa. So I think this is also good. As we have such good results, we can use we can use critical GNI for another features. For example, we can write our own bit set, which compressed in memory and intersects compressed values. Daniel Lemire also provides this codec. It's works fast. Also, Daniel Lemire provides fast decoder for variable byte compressed integers. It also speeds up variable in decoding. Also, Daniel provides native roaring codec, which is implemented in Java in Lucene, but we can speed up it by using vector implementation. Also, we have some ideas how to implement native facet component. It can be done in bitwise manner and vectorized. So it also can speed up our application. Also, as doc values, integer doc values coded by 4, we can implement native doc values decoder. It will decode doc values as fast as possible. That's all. Thank you.